Welcome everyone to our third day of our Altair student webinar series. I hope everybody has been enjoying these so far and been getting the value out of them. Let me introduce myself. I do see a lot of new names today. So my name is Darius Fadanelli, and I'll be your moderator for today's session. I graduated in December 1989 from University of Michigan with my aerospace engineering degree, and shortly thereafter, I actually joined Altair, and I've been here ever since. For many of the years, I used to run our technical support operations, and I had about 40 engineers who I managed with me to establish our technical support, operations. And then the last about 4 years, I've been running our EDU outreach, and my goal is to help students, faculty, and teams get access and know how to use our tools for their projects, curriculum, or student team needs. Also, since we have again quite a few new names here today, let me just go over a little bit the GoToWebinar and what to expect. As you can all see, you're muted. That's so we can have as best audio quality as possible. We have noticed that in the last couple of days, a few people had some audio issues, and what seemed to help most of them, if you go to the audio tab here and pick on that, you'll get an option to change from computer to phone call, and that seemed to work for those individuals, or most of those individuals. And that usually happens when we switch to the presenters. For some strange reason, that some people will lose the audio, and if you do that, you should be able to get that your audio back working. If you do have questions, please use the question tab. Type it in there. Myself or there's our presenters and specialists are here. One of us will answer it. So we, if it's during their presentation, if I can, I'll try to answer it. If not, we'll try to wait to the end, and then we will answer them live so everybody can hear it at that point. All our sessions are being recorded, and these recordings and the amount of files that were used will be available on the same site that you registered for this event. So if you look there now, you actually see Wednesdays and Thursdays recordings, and the files are available. So if you needed to revisit them or forgot something was said, please go there or pass them along to your other colleagues. We have today's session is 2 hours long, and we have some really good topics we're covering here. So the first one, we will have Mohammed, and he'll be covering electric drive concept design with Altair Flux Motor. After that, Patrick will be covering our system dynamics and system controls with Altair Activate. But the key thing, what we're trying to help you guys see from all our sessions, and today especially, that the tools that you have access to will allow you to do multidisciplinary or multiphysics. So this should allow you to be able to have a lot better designs, more robust, more optimal too. So this is what we're hoping you can derive from these sessions, how to make your designs and projects even better. And if you are a student, if your school does not have access to our tools, on our website, under academia, there is the ability to get your free student edition that you can install on your own personal computer. It's good for a year. Key thing is you have to use your EDU email. And at the end of today's session, I'll show how to do that, where you can get access to the free student edition. And also, if you're a teen and if you don't already have access to our tools, we provide them in a free sponsorship in a very simple form that you can fill out and get access to that, all these tools. And one key difference is for our sponsorship, you get the full version. There's no limitations. and you get as many licenses as you need. So whether you need 1 or 50, we don't care. We want to make sure you have what you need and on the workstations you need it to. So if you have any more questions about that, please put that in the question tab and I can answer that. But I don't, I want to continue on here. So the first topic we have, or first presentation, will be for Flux Mortar. Flux Mortar is a flexible software solution dedicated to the pre-design of an electric mortar. It will enable you to easily design your machine from a standard, customized, and parametric parts. You can add windings with a multi-level assistant and attributes for materials to quickly run different types of tests and compare their performance. Flux Mortar, as hopefully you'll see, is an easy to use interface. Very nice environment to allow you to create and do your analysis and reporting and export your electric mortars within a few minutes. As I mentioned before, whenever necessary, you can couple our tools together to enable this multiphysics and do optimization of your designs. Let me introduce our next speaker here and have him get started. I'd like to welcome Mohammed. He got his bachelor's degree in electrical and electronics engineering from University of Khartoum in Sudan. In 2013, he received his master's degree from University Akron in December of 2017, and he joined Altair shortly thereafter in 2018. His expertise is in electric motors design, modeling, simulation, and low-frequency finite element analysis. Mohammed has helped me before in some needs for working with schools and faculty, and I think you really will enjoy his session. So let me change over to Mohammed. Mohammed, I am changing over to your presentation.
Hello everyone, my name is Mohammed Al-Amin and I am application engineer at Altair. Today I will be talking about electric drive concept design using Altair Flux Motor. Here's the agenda for today. So I will start by introduction of electric drive, and then I will move to introduction to Altair Flux Motor, followed by a case study and a demo for the tool. So the transportation OEMs need sustainable technologies to meet customer demands and government regulation, especially with respect to the global warming. So they are looking for safer, lighter, greener, and smarter vehicles. And that's why today we see the push toward e-mobility, which represent the concept of using an electric powertrain. An electric powertrain typically consists of these main components, which are the traction motor, generator, the battery, the power electronics, which includes the inverter but is not limited to it, and the system modeling and control to control the power transfer between all these components. The design of high-end e-motor for electric vehicles is not limited only to the electromagnetic part, but also include other disciplines such as structural, CFD, MVH, and a system simulation. So we need to come with a better workflow to include all this part together to make sure the design meets the requirement. So I will leave you with this short video which explains about this process. So in short, we can break the design into three stages. The first one is the concept design, where we explore a large set of topologies and select the best one which meet the requirement and come with an initial design. And after that, we move into the detailed design, which typically involve multiple physics, including the electromagnetic, the CFDs, the structural, and the MVH. And it's typically the case that we can put all of this under the OEM optimization studies and run them together to come with the optimum and the best design. After that, we move to the system integration part where we include the battery and the inverter as well and make sure all of this work together to meet the requirement. In this webinar, I will have specific focus about the concept design, which is the first stage, in which we have our tool is called Altair Flux Motor. So next, I want to give you a general overview about Altair Flux Motor and its capability. So Altair Flux Motor is a dedicated standalone multiphysics environment to accelerate the design of e-motor concept. It allows fast evaluation of techno-economic performance, which include rapid concept exploration, product visibility check, support users to make a documented decision quickly. It's accessible to broad range of users, which could include and not limited to motor designers, motor integrator, teachers, students, and so on. And that's because it's really has intuitive interface and workflow, and it's really easy to use with no simulation knowledge needed. It has customizable template which are completely parameterized, a user-oriented winding tool, a predefined test with automated reporting, and you can literally build, machine, test it, and produce the report in a matter of minutes, not hours. It's really fast and accurate. It's used mixed finite element solver in the background and also some analytical calculation with embedded modeling knowledge about e-motors and also optimization process in the background. It has effective machine part management. There are standard libraries provided with the tool, cover a large set of motor topology, including the slots, magnet, and bars. Again, all of these are parameterized, and even if you don't find specific shape you want, you can actually customize and create your own parts in Flux Motor. And it also includes efficient project management. You can access quickly your past studies. You can categorize them into different catalogs. You can have quick performance comparison and ranking between the different designs. It also allows you to, after you come with your finalized e-motor concept design or initial design, it allows you for further connection for advanced studies. So flux motor is mainly for the design of radial flux machine, which cover more than 90% of the motors in the market today. So it can do synchronous machine with permanent magnet with inner or outer rotor. And it can also model induction machine with square cage with inner or outer rotor as well. And with the possibility also to add skewing to the slot, magnet, and bars. And there's more machines types to come in the future. The next release of Flux Motor, which is in November, December this year, will include the synchronous reluctance machine, for example. So what are the tests that are available in Flux Motor to evaluate electric motor design? So as I said before, in Flux Motor, there's no need to put any effort into the post-processing, and the results are automatically illustrated after the test is finished. So from electromagnetic point of view, we can run an open circuit test and look at the back EMF test and the cogging torque. And we can characterize our motors that give us a different maps in the ID, IQ range. We can also run a data sheet test to find the corner point or the base point of the motor, giving limit on the current and the voltage available. We can also run and see the performance of the motor at specific working point. And we can also run our motor across the entire speed range and see the efficiency map and its performance. On top of that, we can also evaluate at duty cycle defined by speed and torque against time and look at things like what are the average losses during the duty cycle and what are the average efficiency. During the design of electric motors, we should make sure that the temperature inside the motor doesn't exceed a specific limit. Otherwise, we are risk damaging the motor. And for that reason, we have to make sure that we are designing an efficient cooling method to extract the heat out of the motor. So flux motor allow you to design different housing with fins and or cooling circuit and apply different external and internal cooling. And then it allow you to run a steady state thermal test to look at the temperature distribution along the different parts of the motor. In this case, the heat source will be provided as a set of losses in the stator, rotor, and the winding of the motor. It also allows you to characterize the thermal network of the motor provided by different thermal resistance between the different components inside the motor. And it also allows you to get the losses directly from one of the EMAG tests already performed in flux motor and use it as a heat source in the thermal test, or do it in iterative process where you actually run the EMAG to get the losses, provide it as a heat source to the thermal part, and then run the thermal part to get the temperature and update the material properties and run the EMAG again, and then follow this process until it reaches convergence. Also in the next version of flux motor, the transient thermal will be available. Flux motor also allow MVH prediction in the early concept design phase, although these are just preliminary results and it's not as accurate as the complete FEA solution, but it can give you a great insight into any future problem or issue. There are two different tests you can run. The first one is the single working point test, where you can get results such as the model analysis, the radiated sound power, and the electromagnetic forces on T's. You can also run the test across the speed range and look at the radiated sound power versus speed and frequency range, or what's called the waterfall diagram. Or you can look at the order cut analysis and see which order is contributing the most to the noise. Or you can look at the overall weighted radiated sound power versus speed. As we have seen in the introduction part, once you are finished with the first stage, which is the concept design, you want to move to the second stage, which is the detailed design. So flux motor allows a connection for advanced studies, which include flux, which is our full-fledged electromagnetic FEA tools. So in Flux, you can do all type of advanced electromagnetic analysis, which is not possible in Flux, such as eccentricity analysis, demagnetization, short circuit, compute electromagnetic forces, and export it for other mechanical tools. So in this case, the model will be fully parameterized in Flux. All the physical properties defined in Flux motor will be embedded, and the model is really ready to be solved and post-processed in Flux without anything defined from the user. So in a way, you can think of Flux motor also as a preprocessor for Flux. It also allows the connection with HyperStudy, which is our design of experiment and optimization tools. And in there, you can run directly the optimization using Flux Motor as a solver. And indeed, you can actually access all the runs in Flux Motor if you want to look further at the result. You can also optimize the motor not only in a single operating point, but optimizing considering the full duty cycle, which make more sense on electric vehicle application. Flux Motor also allow you to export an FMU, which is stand to functional mockup unit. It's a format which is accepted with many system simulation tools such as Activate or other environment, and it allows you to have a reduced order model instead of running a cost simulation with high fidelity, which takes a lot of time. So now we know about Flux Motor and its capabilities. Let's look at one case study in how Flux Motor can be used. In this case study, we want to design a new EV motor with the goal to optimize the efficiency of the motor over the entire duty cycle. In this case, the duty cycle is based on WLTP, which shown to the right here, defining by different speed and torque requirement at each specific time during the cycle. The design variables here are to modify the rotor shape only, with the stator shape being fixed. And of course, we need to keep the requirement needed from the motor as a constraint on the study, which is the base torque should be greater than 180 Newton meter and the base speed greater than 5,000 RPM. So here's the workflow that we can follow to optimize the motor efficiency over the entire duty cycle. So starting from the specification we come with the initial design. For the initial design, we evaluate the efficiency and use that as our baseline. And then we run several iterations for DOE and optimization over the initial design, or starting from the initial design to come with our optimum solution, and then evaluate the optimum solution over the duty cycle and then compare it with the baseline. So here is the first step where we start from the specification and we come with the initial design, which you can see to the right here, with the stator outer diameter of 180 millimeter. The length is 25 millimeter. Number of stator slot is 54, and the number of poles is 6. And then we have this initial design modeled in Flux Motor, so we can put all of this through the design tab here by following a step-by-step process starting from templates, and the model will be automatically parameterized. After we put our initial design, we can run the performance mapping test to come with the efficiency map, and then we can evaluate the average efficiency over the duty cycle, which in this case is around 71%. And Then from the initial rotor shape, we have around 22 design variable in the rotor part, which we can use in the DOE and optimization studies. The performance to be maximized again is the efficiency over the duty cycle, and we should respect the phase current not to exceed 280 amp, and this limitation, as we see coming from the specification, and it's really limited from the inverter side. So the DOE will help evaluate the different design variables to understand which one has a dominant effect on the objective and the constraint. So using this result, 10 design variables over 22 can be screened out from the optimization study. In the optimization studies, run around 50 runs with 5 multi-execution, and all of this can be done within 1 hour. And the optimized duty cycle machine efficiency increased by almost 3% from 71% to 74%. And also on top of that, the optimized design save around 32% on magnet mass. So these case studies kind of show the power of flux motor, where you can actually explore a lot of design correctly in a short amount of time. Now I will show you how flux motor actually works through a demo. So in this demo, we'll be designing a PM motor for electric powertrain to meet the specification on the table on the left here. So from this specification, we typically go through analytical calculation to estimate the main dimension of the motor. In this case, I have a stack length of 150 millimeter and the stator OD 198 millimeter, and then we have to decide on a basic selection, which includes the rotor topology, the slot pole combination, and what is the material to be used in the design. So starting from this table here, we will start putting the data into flux motor. So I will start the demo by opening the most recent version of flux motor, which is 2020.1. So the main interface of the flux motor allow you to start building a new motor. You can see the different type available here. It also shows you the most recent op-amp motor in the bottom here. In the left side, you have the help and the resources down there, and then you have different user preferences to use from, and then you have the unit, which allow you to change the unit which you will have the inputs and the outputs inside flux. For example, you can have the dimension put in inches instead of millimeters. Then you have the script factory. This is something which is still in beta mode, but basically the idea is to allow you to use scripting to design your motors instead of using the GUI. The material manager has all the reference materials available inside flux motor. It also allows you to create your own materials. The part library, you can go and explore the different standard parts available and also modify them if needed, and building your own parts. The motor catalog is an environment where you can save your different designs and put them in different catalogs and compare them together. So in this case, I will start with the motor catalog. So the motor catalog include all the different design. There are some reference catalog included as an example down here, and the user catalog are in here. So if you select specific catalog and specific motor, you can see general data about the motor directly from here including its dimension and main information. And if the tests are already solved in this design, you can also look at the performance. More, you can actually compare two different motor design together. So what you need to do, you need to select the specific motor design that you want and add it to the comparator. You can add as many as you want, and then basically click on compare, and this will put all the design you added side by side, so you can compare either the dimension or the performance of them together. And you can also do ranking of the performance if needed. So in this case, I already put the information about the design I specified earlier, and I will go ahead and open that design and guide you through the different inputs we need to build the motor in Flux Motor, and the different tests that we can run in the motor. So I put this under this catalog, and here's the motor I'm going to use for demo. So I can just double click on this motor, and it's going to open a new environment which called the motor factory. And this is where we can do the design, test, and export of our design. So in this environment, the first thing you will notice that we have three tabs here, starting from the design, where we put the dimension and the information about the motor. The next part is the test with current different predefined test in Flux Motor, and the third part is export. So starting from the design, the workflow is always to go from the left to the right. So again, as I said, all the input are already defined here, and what I'm going to show is basically go through this different input to understand what it means. So the first things about how this GUI is defined, you will always see that the input is in the right side, then you have the view in the middle, and then you have the output in the left. And using the output, you can actually go through different part of the view. So the first thing we are going to do is to put the main dimension of the motor. There are different inputs mode you can select from. In this case, we are selecting the inner diameter to be the resulting dimension. So we start by putting the OD of the stator, the length of the motor, the number of slots in the stator, the air gap length, the OD and the ID of the rotor, and the number of poles. And all of these are actually computed analytically during the initial design stage. Once you put that, you can apply the input. So the next part is to go to the housing, and this part is needed specifically if you are interested on the thermal result. Otherwise, if you're just looking at the electromagnetic result, you can ignore the part about the housing and the shaft as well. So we start by first selecting our frame type. So you can select circular or square frame, and you can put the dimension of the thickness and the extension of the frame in the connection side, which shown here as CS, or the opposite connection side, OCS. Then you can add fins if you have any in the motor. We don't have one in this design. And then you move to the cooling circuit. So this motor will be liquid cooled due to the high power density in this motor. And in this case, there are different types of the cooling circuit, the zigzag type and the solenoid type. In this case, we will select the solenoid type. This can have a circular cross section or a rectangular cross section. We'll go with the circular cross section, and we have around 12 turns around the water jacket, and you can put the dimension of this of the cross section, which is 5 for the height and 5 for the width as well. So once we are done with the housing, we move to the shaft, and we can decide to have a shaft here. As I said, it's important for the thermal point of view because it can extract some heat of the motor. So this information we have about the shaft, and we can also include the bearing here as well. So in this case, I'm actually completely using the default dimension. I just adjusted the extension for the shaft to be the same as the housing. Next part is to move to define the rotor shape and specifically the magnet. So as I said, Flux Motor come with a complete set of standard libraries to choose from. For example, you have libraries here to cover the ring magnet for an SPM type of motors or V-shaped magnet for interior magnet type of motor. So in this case, we have we'll select a delta shape for the magnet, which included under the layer libraries, and the name of the part is 10A. Once you select the part, it will come here and you can see a view of it, and it will come with the default set of inputs, and then you need to adjust these parameters to the shape that you want. So once you put your cursor over any parameter, it will show information what this parameter mean. It also show a graphical representation of this parameter in the view here in the middle. Once you put all the information, you can validate your part and you can see the update directly here in the middle. In our case, we don't have the skew, but if you have some skew, you can add it through this step here. The polarization indicates the direction in which the magnet is oriented. So all the standard magnet that come with flux motor had a default polarization, which is typically right, and you don't need to change it. But if you want, you can use this input here to change the direction of the magnetization. The next part is to define the stator parts. So it's the same idea. There's a large set of standard library to select from, including free shape, parallel slot, and parallel tooth. In our case, we are going with parallel to 01F part, which include the following parameters here. So we need to go ahead and define those parameters. Also, there are some hand calculation which can be done to at least find the thickness of the yoke, the width of the teeth, and so on. So it should be available beforehand, or you can just try to estimate them based on the motor dimension. And then you validate the input. You can also add the skew if you want to the stator part. Next is the winding tool. And the winding tool is actually one of the most powerful tools in flux motor. So here you start by defining your winding connection, either star or delta connection, and then there are different definition mode depending on what you want to do. So based on the slot port combination, flux motor will come with an automatic layout for the winding. But if you want more freedom, you can move to easy, advanced, and expert, where you can actually define the winding layout completely by yourself by defining the in slot and out slot for each coil. Once you define the main winding layout, you go and define the coil in the slot. So you can define the wire topology as either circular or rectangular. So in this case, we are using a hairpin winding, and so we'll go with the rectangular cross section. And then you need to define the number of turns per coil. This is typically computed based on the available voltage at the terminal for the motor, and can be done computed to target a specific back EMF. So in this case, we have 6 turns. Number of wire in hand is 1, and this is the wire dimension. You can also put the insulation thickness between the wires for the liner, for the phase separator, and so on. The next part includes end winding of the motor, and by end winding I basically means those two parts here. Those are important to define. They are typically not adding a lot to the electromagnetic performance of the motor, but they will add to the coil resistance and they will add to the joule losses produced by the coil. So you can define this as U shape or C shape and then define the dimension you want here. The next part is the X factor is used for calibration. Let's say you have some measurement and what you are getting from flux is not exactly matching due to some environmental effect in the measurement. Then you can come here and use this calibration factor to adjust the value. You can also target specific reference temperature, which you know the motor will be operating in, and then to see the resistance of the motor at that specific reference temperature. The next part is only important for the thermal performance. So it's actually the potting or the encapsulation of the winding. It's typically the case on this high-end motor. It prevents the coil vibration. It help insulate the coils from the stator laminated part. And it also help in extracting the heat out of the winding or the coils. So in this case, we are defining the potting, and we are giving the dimension for the potting extension. Once you define the input for the winding, you can look at the winding layout. And let me remove the input side so we can see it better. So we can see a layout of the winding here. We can see a radial view of the winding. We can see connection table, expect each coil and what is the input and output slot for it. And most importantly, we see criteria to be able to judge our winding layout. So we look at the magnetomotive analysis, which show you the force produced by the coil in the air gap. So you want this to be as sinusoidal as possible, but that's not possible due to the slotting in the stator. So we typically look at the FFT analysis of this MMF waveform and try to reduce this harmonic distribution contribution as much as possible and just leave the fundamental. Another criteria is the winding factor, which give you an idea of the utilization of the cover. So you want this winding factor to be as close as possible to 1. So in this case, it's 0.96. So that's good enough. Once we decide in the winding, now we can move to define information about the cooling. So first we go to define information about the external cooling. So the first thing is the fluid one. So in the external to the surface, in this case, we have just natural convection and the machine is oriented in the horizontal direction. For the cooling circuit, you can define this parameter in different ways. In my case, I'm using convection coefficient inside the water jacket of 12,000, but you can define the fluid velocity and the flow also if needed. Next, you can define the radiation, which typically auto is a good one. But if you want to control it better, you can use the user mode. And again, X factor is just for calibration. For the internal part, what you need to define either to define a natural convection or a forced convection. In this case, I'm defining a forced convection here in the end winding part. So you need to define the tip speed ratio, which is the ratio between the rotor tip speed and the internal fluid velocity inside. So I just went with the default number in here. And again, you can define the radiation, but in this case, I left it as auto. And the interface mode between the different part of the motors. So you can calibrate that if you want it. So in this case, I'm just using uh, auto in this case. So the slot connection mode is going to show you what are the model which is used to model the winding from thermal point of view. So in this case, we are just using harmonized thermal conductivity. The last part of defining the on the design part is to define the material. So in this case, we are using stainless steel for the housing, for the frame, the shaft, and the bearing. So it doesn't have any electromagnetic properties. For the rotor, we are using NDE FEP 1050 2800. So it had a remnant flux density of 1.05, and the corrosive field is 2800 kiloamp. And for the rotor and stator magnetic circuit, we are using M33035A. And for coil, we are using copper. For insulator, we are using Nomex. And for the cooling circuit, we are using water. And the external cooling is air. So once you define this material, you can click on this one, and you can change the material if you want. So this shows you all the available material in the libraries, and you can also go to the material manager from here to define your own material for the design. Once the design part is done, you can move to the test part. So the first thing is the characterization test, and we start with the open circuit test. So there are two tests available here. The first one is the cognitive torque test. And you can actually saw an overview here about what this test means and what type of result you'll be expecting from this test. So in a permanent magnet machine, the magnet has tendency to align with the slotted stator part, and this is create what's called a cooking torque. That's a torque you can feel actually even if you move the rotor freely. These torques typically need to be minimized, and because otherwise when you load the machine it can cause significant torque trouble during the operation. So you can put the information for the cooling torque. Typically you don't need any inputs for this test, but you can change the magnet temperature if needed. And the result you get from this test is the waveform for the cooling torque, including the peak-to-peak information and also an FFT of the waveform of the cooling torque. The second open circuit test is the back EMF test. This test is basically you rotate the machine with a fixed speed and you look at the voltage at the terminal of the machine. So the only input you need is the speed. Again, you can change the thermal setting in this test. And what you get out of this text, typically different waveform for the phase voltage, the line-to-line voltage, and also the breakdown of the harmonic content of this waveform. You also get the flux density in the air gap and also the saturation on the stator and rotor parts. So you typically want to do this test to make sure that your back EMF is not exceeding specific limit. You want your back EMF to be 20% or 10 to 20% lower than the available voltage at the terminal of the motor, so that you can actually push current inside the motor. The next type of test is the model test, and in this test used to characterize the machine basically. So the input is the maximum line current that you can provide to the machine, which is 300, and the maximum speed that this machine can go, which is 15,000. And then there's a bunch of settings, including the thermal. So you can set the thermal in the winding bar and on the magnet. The electronics to include the losses in the power electronics, and the mechanic is to include the mechanical losses. In this case, you just define the mechanical losses at one speed, and then we have an analytical model which will scale it down for different speeds. So once you run this test, the main result is different map for the flux linkage in the DQ uh, uh, range. So, and those maps can actually be exported to be used as a reduced order model in other system simulation tools. The next test is the datasheet test, and this test is basically intended to find the what's called the corner point or the base point for the machine, which is defined here. It's actually the maximum speed where you can keep the maximum torque of the machine. So in this test, again, the thermal and the mechanics setting can stay the same as before, but in the electronic, there's something new. So we can define what is the available DC bus voltage. And based on your inverter control strategy, this will be scaled down, and Fluxmotor will compute the maximum line-to-line voltage available to the motor. So the result you get from this test is base speed performance, including the speed of the corner point and the mechanical torque and the efficiency. You also have information what is the optimum control angle at that operating point. You also have a lot of information, but more importantly, you have a breakdown of the losses in here. You also have information about the torque ripple that you will have in the machine, and also breakdown of the torque ripple as a percentage from the average torque. The next test is the steady state thermal test. And again, this used to evaluate the temperature distribution inside the machine. So the main input here on the thermal setting, you can put the temperature of the external fluid and the temperature of the fluid in the cooling circuit. And you can put a set of losses here. So you need the losses in the stator, such as the Joule losses and the ion losses. And you can also include the losses in the rotor part, in the rotor lamination and on the magnet, and the mechanical losses as well. So you can input this yourself, or you can import it from other tests, other electromagnetic tests that are already performed. So the main result you get is the temperature distribution on the different part of the motor. You get a radial view and axial view as well. And you can also get the main parameters defining the thermal network of the motor. The next step is the sine wave test, and this can be defined in two modes, either motor or generator mode. And you can also do, in motor mode, you can do three different ways. You can define your current control angle speed, and it can give you what is the torque and what is the efficiency, or define specific torque speed point you want, and it give you what the current and the control angle needed to reach that operating point. The next one is the square wave test. It is something specific for 6-step inverter drive, where the current has a trapezoidal waveform rather than a sine waveform, which is not the case here, but just let you know this is available if needed. The next test is the performance mapping test, and this is intended to find the torque, speed, envelope of the machine, or mainly to find the electromagnetic performance across the entire speed range of interest. So the input here is stay the same as before regarding the setting, and in the input here you put the maximum line current. The maximum line-to-line voltage will be deducted from the setting you put in the electronics, and then you decide what is the maximum speed. Let's say for some reason, because the available voltage is not high enough, you cannot reach this maximum speed. You put here is actually going to give you a warning message, and it's going to tell you what is the maximum speed you can actually reach with that voltage. On the setting here, you can also include a duty cycle, and you can define it in here. So you can define it yourself, or you can actually load the file, Excel file in a specific format to 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 fetch this information and put it here. So once you run this test, this is the result you'll be expecting. So you get information about the base speed, which you expect to be the same as the datasheet test before, but also you get information about the maximum speed, including the torque and the efficiency you can reach, and also all the losses breakdown. You can also get the different curve, including the torque, speed, envelope. You can also get different map, including the efficiency map across the all speed range. And you can also get different curve related to the specific duty cycle that's we uploaded during in the input part. Okay, so we can track how the efficiency is changing during the duty cycle. And if you go back to the tables, you can actually find this information, and you can find the average efficiency during the entire duty cycle, which is in this case is 95. So the next test is the MVH test. There are two tests you can run here. The one is just the MVH in a single working point defined by the current, the control angle, and the speed as here. The result you get here includes the model analysis, which show you basically the different mode shape and their natural frequencies. You also have the Maxwell pressure in the air cap, and you have the radiating sound power, either across the different order, or you can show this against the frequency. You also get the electromagnetic forces acting on the stator teeth, which is the main source of vibration on the stator housing assembly of the motor. The second test in the MVH is the spectrogram test. And the operating points here can be defined in two different ways. So you can define the different points with the current, control angle, and speed, as shown here in the table, or you can import your own table. Or you can define, take this point directly from the torque speed envelope. So in this test, we define the setting is almost the same as the performance mapping test. So we put the maximum available current and voltage, and then we run the test. So first it will run electromagnetic test, and it will come with this torque speed envelope with different operating points in here. So those are the points where the MVH will be evaluated. And then it will evaluate the MVH and give you results such as this one, which are waterfall diagram, included the radiated sound power versus frequency and speed. So from this curve, we can already notice there are some issue around or the maximum radiated sound power is around 6,000 Hertz at almost 7,500 RPM, and near the maximum RPM was of 15,000. We can also look at this graph, which show the order cut analysis, and you can look which order is contributing the most to the noise. So in this case, it happens to be order 48, which is expected for this type of topology because it has 48 slots. And then you can look at the overall radiated sound power over the speed range. And in this case, we can see that the maximum is actually happening at 7,500 and 15,000 RPM. So they give you a great insight where you could have a high noise, and you can go ahead and try to adjust your design for the motor or either the housing to try to avoid this problem later on when you go to the detailed design part.
All right, thank you, Mohammed. That was a great presentation. Now, if I'm just going to reshare my screen here. So we do have Mohammed available to answer some questions. So if people do have questions, type something in the question tab and Mohammed can answer them for us here. So great to have him in person here so you can be able to get the answers from him. Mohammed, is there anything additional you wanted to add to your presentation while we're waiting for see if any questions come up?
Yeah, there's nothing specific, but just due to the time, I didn't cover the last part with the connection to other tools like Flux and HyperStudy. But that's so if you have any specific question about that, feel free to let me know.
Yeah, good point. And as I mentioned before you started it, the tool can connect to the other tools that we have, and then of course, to do optimization. There's a lot you can do, but really the point was to get people started to see what's possible at this point. So here's the first question. I'll read it, and then you can answer it, Mohammed. So, is there a module for analysis for permanent magnetism, like neodynamic components? That comes from
the material for analysis of permanent magnetism, like neodymium component. I didn't understand the question completely, but I think about when you actually during the process of manufacturing the magnet, where you basically bring the raw material and then you magnetize it or polarize it in a specific direction. Is that what you mean? So that's very specific, and we cannot do that in flux motor. Flux motor is really dedicated to electric machines itself. But this process you're talking about can be simulated with our more general tool, which is Flux. So I hope this answers your question.
Good point. We do have two tools with the name Flux Mortar, and just Flux, which is the more general purpose tool. Flux Mortar is a very specific interface for, like I said, electronic or electrical mortars and devices. So again, it makes it even easier, the workflow when using Flux Mortar. But that's so Flux can do what you mentioned there.
Yeah.
Well, good, Rodolfo. If you do have a add-on to that question, please put it in here. But if not, I'll give just about a minute more, and then we'll move on to the next presentation here. So, right, I don't see an additional question there. So, thank you so much, Mohammed. And again, if you can stick on for a couple more minutes to see if anything else pops up, that would be great. Just answer that in the question tab. But we'll move on. So, as one of the things I mentioned, again, is this whole connection of our tools and this multiphysics, as you saw in one of the previous slides with the different animations indicating different type of simulations being done. And of course, mortars was one of them, but we had other things that were being shown there as the multidisciplinary or multiphysics neat things that you can do with HyperWorks. And the next discussion presentation that we have from Patrick will cover our controls and systems and our math-based tools and how they can help you achieve that. And if you kind of see in this slide here, the math-based tools, which is, I know most people are familiar with MATLAB. We have an identical tool called Compose. It reads the .m files, and the syntax and format is identical. So you basically, if you know MATLAB, you can just start proceeding from there after you read in your file. Also, we have our control system block diagram tool, and then they all connect so you can with your 3D simulation. And again, I don't want to take too much thunder away from Patrick, so I just kind of want to show what we mean here, and hopefully this gives you a little bit of understanding of that, and hope kind of teases you to see what Patrick will be showing here. But so again, Altair Compose software is an environment for doing those calculations and manipulations, visualizing your data. And you can do programming and debugging of your scripts. Therefore, your useful repeated computations and process automation. So just like in other tools out there, it allows you to perform a wide variety of math operations, including linear algebra, matrix manipulations, and differential equations, signal processing, control systems, polyfitting and optimization, and many others. So at the end of the day, it also helps you to make those better engineering decisions. The other tool that works along here, Activate, is also an open and flexible tool for rapidly, modeling and simulating your products in the form of 1D models, signal-based or physical block diagrams that you can connect to your 3D models. You can leverage a flexible spectrum of simulations throughout your development cycle. Allows you to ranging from early conceptual design with models involving more abstraction or typically shorter simulations to later detailed design. So, but it's really the connecting glue point here. Well, I'll let Patrick go through all this in more detail, but just want to give you a little primer what to expect. So Patrick, he's one of our application specialists that we have here. He's primarily focused on Activate, the Compose tool, which is the math and scripting tool, Motion Solve, which is our multi-body dynamics tool, and he supports a variety of industries, specifically automotive, aerospace, heavy machinery, agriculture, consumer electronics, e-mobility. So good fit to a lot of type of projects students are now doing today or the student teams are doing. Without further ado, I am going to switch over to you, Patrick.
Hi, everyone. Thanks very much for joining today. My name is Patrick Goulding. I'm an applications engineer with Altair. And I'm going to be talking today about our system modeling and system integration tool, Altair Activate, used for modeling system dynamics and controls. So our agenda today will be in about a 40-minute webinar to go over an overview of Altair Activate, and then talking about physical component modeling, specifically mechanical system components using Modelica, which are a set of blocks that we utilize with Altair Activate for physical component modeling. And then we're going to talk specifically about vehicle dynamics, how to model vehicle dynamics in Activate in sort of a low-key level, and then taking that model that we use as an example and putting it into a larger context, a slightly more complex model for management of energy consumption in a vehicle. And then I'll just close out with some learning resources that you can utilize for learning a bit more about in-depth of modeling, system modeling with Altair Activate. So what is Altair Activate? Activate is a system modeling tool, yes. It is also an open integration platform. And we like to make sure that our users understand that it can and should be used as an integration tool for subsystems designed in various disciplines, and also designed using various tools. So you can design subsystems in Activate using a mathematical approach. using just scripting, and it embraces many languages for scripting. C code, Spice for electronic modeling, component modeling, Modelica for physical components, Python, and our own open matrix language, OML, which is a matrix-based language for mathematical scripting. And also the approach for modeling that may first come to your mind with system modeling would be the block diagram approach, or a 1D approach, we like to call it. So this would be utilizing signal blocks for the sharing of, or the connection of signals between blocks, creation of a signal using those values entering as input into another block, output another value, and so forth. Also physical component modeling using Modelica, and electric and electronics using our set of Spice blocks as well. And with Altair Activate, you also have the opportunity for co-simulation with our multi-body dynamics tool, MotionSolve, also with our low-frequency electromagnetics tool, Flux, and utilizing the functional mock-up interface, or FMI standard. You can co-simulate with any outside third-party tool that embraces the functional mock-up interface. So any other third-party tool with which you could export a functional mock-up unit or a subsystem, you can bring in that functional mock-up unit into Activate and co-simulate with that subsystem as well. So many different domains or ways in which you could model systems or subsystems in Altair Activate, and you can bring them all into one shared diagram. So in this regard, it is an integration platform that also incorporates linearization of subsystems and ways to use optimization as well. This idea of modeling in a 0D, 1D, or 3D manner, I'll talk about a little bit in the upcoming slides. Just to hit on it again, 0D is the sort of mathematical approach, or a system of equations to represent a mechanical system, let's say. A 1D approach would be that drag and drop block diagram system modeling sort of way. And then the 3D would be if you're co-simulating with a model-based tool, a 3D model, and using that as a subsystem in your system model. Using these different types of modeling, 0D, 1D, 3D, you can design all types of systems in Activate, from multi-body dynamics to control systems, motor control using low-frequency electromagnetic analysis, and high-frequency electromagnetic analysis as well, bringing in output results from our tool FICO for high frequency, as well as structural analysis, bringing in flexible bodies in MotionSolve. There are various reasons that you might want to design using a set of mechanical equations for a multi-body system versus a 1D signal-based approach versus a 3D co-simulation. If we're thinking about multi-body dynamics, this set of equations would look something like this, scripted using our open matrix language. But you can choose to model that exact same system using our Modelica library for physical mechanical components, and that would look something like you're seeing in the middle here. And for the highest fidelity solution, we're talking about bringing in a co-simulation, a motion solve block, with a mechanical system designed in motion view using motion solve, and then sending signals co-simulating with that mechanical system for your highest fidelity analysis. So let's take a look at the user interface for Altair Activate. It's very user-friendly, I believe. The ribbon on the top allows you to open new models, and using that view drop-down menu, you can see the different windows that are available to you in the user interface. A project browser, a property editor for editing things like the color scheme of plots of your signals, a variable browser, and a really nice demo browser on the bottom left, which is a great way to explore the tool by pulling in, bringing up some of our demo models organized in various domains, so you can get an idea of how you might go about building a similar type of model. There's a command window, an OML command window at the bottom for scripting with Open Matrix language or Python as well. And then our palette browser on the right, so you can navigate through our sets of blocks, like this constant block for generating a signal of a constant value, step generators, sine waves, and so forth. And this Modelica browser for our Modelica components. And those are subcategorized into electrical, mechanical, magnetic components, and so forth. And so I'll just pull in a couple Modelica components as an example. This is a spring and damper. And then you can connect things like the spring and damper to a mass for defining a mass that is acting on that spring and damper. And your modeling window allows you to navigate through the several levels of your model. This is a hierarchical modeling approach, so you can zoom in to subsystems and back out again, and then connecting your inputs and outputs with your linkages. So let's take a look at an example of a mechanical model in Activate. So we're going to use the example of an active suspension. If you're going to model an active suspension in Activate, you can start with what we call a quarter car model, which is zooming into, instead of all four wheels, zooming into just one wheel system. And looking at the diagram on the right, we can break this down into 4 simple equations that define our system states. And the system states that we're interested in this example are really a set of 2 different displacements and 2 different velocities. So our tire deflection is the difference between the displacement of the road and then the displacement of our unsprung mass, which is the first mass above the displacement of the road. And then our unsprung mass velocity, which is the rate of change of that displacement over time. And then the suspension stroke, which is really the displacement of the suspension mass. And we define that as the difference between the displacement of that sprung mass and the displacement of the unsprung mass. And then the sprung mass velocity, the rate of change of that sprung mass. So if we look at a system model of this active suspension, that diagram of the sprung and unsprung mass of really those 4 states is enveloped in this blue block there, the quarter car model, that also encompasses the control system as well. So if we take a look inside that blue block, sort of zooming into that block, we'll see our suspension system, which is modeled using Modelica components. And it looks very similar to our diagram, right? And that's because of the way you can utilize Modelica blocks, the way they interact and share information with each other allows you, it's an acausal way of modeling, but it allows you to make your system look very much like it would in sort of a diagram that we saw. So included in this Modelica system, we see our road velocity input, our road velocity signal coming into our system here, outlined in yellow. And then that suspension system, like I talked about, looking exactly like our diagram. So we have blocks for our masses that define our masses, and double clicking on those blocks will allow you to set the parameters of that mass, which is just a value of the mass. Our two spring and dampers, and double clicking on those allows you to set the spring coefficient and the damping coefficient. Our actuator force, which is the signal coming in and acting on the upper suspension, the sprung spring and damper, which is our control force, and that makes it an active suspension rather than a passive one. And then we're measuring these three things: our suspension stroke, our sprung mass velocity, and our sprung mass acceleration. So using this approach of utilizing Modelica physical component blocks in order to model an active suspension, compared to if we used a 3D model, a co-simulation with multi-body dynamics 3D tool like MotionSolve, it allows us to run this model very quickly and to run many iterations of this model in order to, for instance, tune a control system. And when you're tuning a control system, if you have experience doing so, you know that it takes many iterations, many times running that model in order to measure the response of your system, and then to tune it a bit further, tune your control gains. So you want a model that runs very quickly, and Modelica models run quite quickly, and so do a mathematical 0D model as well. So this is a case where the fidelity of the system that you're modeling can have a large impact on your ability to design your control system. So your output for something like this to measure the effectiveness of your active suspension system would be measuring the sprung mass accelerations using, in this case, 3 different types of an active suspension. Active suspension with soft, moderate, and firm gains. And so you can measure the response of your system and decide what are the best parameters of your active suspension system. So now let's take a look at modeling some simple vehicle dynamics in Activate. So if we're talking about vehicle dynamics, let's break it down or distill it into just sort of the simple vehicle dynamics. So a summation of the forces that we're interested in. And then we'll add in some real values here and then take a look at a system model in Activate of this. So the forces that we're interested in are the driving force, which is coming from the engine, right, producing torque and driving the vehicle forward. And then the forces working against it, which are a braking force when the driver is applying a brake, the force due to friction, which is the tires against the road, and then the drag force of the air acting against the windshield of the vehicle. So this makes up sort of the summation of forces that we're interested in modeling. So for instance, if we take a look at the driving force, we have our driving torque. We're giving that a value of 200 Newton meters. And then we're taking into account the wheel radius, because the driving torque multiplied by the inverse of the wheel radius gives us our forward drive force. And then we break down the braking force, the rolling friction, and then the drag force as well here. But let's use these values and then take a look at a system model that incorporates these. So here we are in Activate. This is Activate, the latest version, 2021.1. And we have here a system model of a vehicle with input of a driving cycle. So this is a speed versus time drive cycle that's going to command this vehicle to move while the vehicle experiences the dynamics that we saw in the slides before, the forces against it due to friction, braking, and drag force. And then this vehicle, we're going to measure the energy consumption for this vehicle to follow this drive cycle while under the influence of these external forces. So I can go ahead and play this. I can run this model up in the top ribbon using this play button. And when I do so, this model pulls up a little user interface, a little GUI, with which I can use to enter the parameters of the vehicle. So the mass of the vehicle, the aerodynamic cross-section that's used in the calculation of the drag force, the braking force, and so on. And when I hit OK, it runs this model, and I can see that it ran very quickly, and it's output my results here. And the results that I'm mapping, for one, this is the drive cycle on the top, so the speed versus time, and then the energy consumption in kilowatt hours across the distance traveled. So let's take a look inside this model and see how we came up with this and see how it's modeled. So I can zoom into this car subsystem and see that it starts with a driver. And if I go into this driver block, I see that I have my input signal, which is my drive cycle, the desired speed, the velocity of this vehicle, and then a simple KI controller, a PI controller, proportional and integral controller, in order to sort of for this that models the engine to maintain the desired speed with our actual speed, to match our desired speed to our actual speed, and try to maintain that while the forces acting against it are occurring. So those are the disturbances. And then our driver applies basically an acceleration, the gas pedal, and sends an acceleration signal to our engine subsystem. So we can look inside that. And we have a simple engine, which is modeled using Modelica blocks. And again, I'll show you on the palette browser on the right side, we can go into our Modelica block library. And these are mechanical blocks pulled from the mechanical set of blocks, and translational. And then if I go back again, go into the rotational and components, and we can see some of these blocks that were used to model the engine. So this is an inertia block, we have a torque block, which converts our torque signal into a torque applied to our small mechanical system. And a lookup table here. So we have our accelerations coming from our gas pedal, which is going into a lookup table, which is an acceleration versus torque table. So from that, then the output of this will be our torque applied. So output from our engine subsystem, we have our rotational velocity of essentially the drive shaft between these two blocks here. And our rotational velocity signal enters into, as input, into our differential. So we can take a look at our differential, modeled again with rotational mechanical blocks from the Modelica library. So we have our input rotational velocity signal coming in here, moving into an ideal planetary gear. And using this and a couple other inertia blocks, we have our differential modeled, which then essentially, splits our rotational velocities from the drive shaft to our two wheels, our right wheel and our left wheel. Moving into those, what does a wheel do? It turns rotational velocity into translational velocity, and that's what we see here. So another lookup table, which is used to turn our brake signal from the driver into an opposite force. So this is our brake force applied against the the forward translational force applied by this rolling wheel block. And then our friction force as well. So we have a block here, which is support friction, which applies friction based on our parameters of friction, working as well against the wheels, against our driving force. So output from this wheel subsystem is our translational speed. Okay, so now we can measure our forward speed of the vehicle, which is a summation, the forward speed, using or taking into consideration friction and our brake force here. So you see how we're adding together, we're compiling sort of our dynamics, our vehicle dynamics, our set of four states that we saw in the previous slide. So now moving to the right in our system diagram, we have our driving resistance, or our drag force. So here we have an equation which calculates based on air density what the drag force would be, and it's applied, is fed into a force block, again working against the vehicle mass and our translational speed. So in this block here, in this subsystem, we incorporate the drag force working against the vehicle and outputting our vehicle speed that's now incorporating our drag force as well. So if we zoom out again and zoom out completely, our vehicle speed is now fed back into our driver as our actual speed. And so the driver, that sort of simple control system in the driver, is taking into account our actual speed and trying to match it to our desired speed. So we've used this model of a simple vehicle in order to measure the energy consumption during a drive cycle. Now let's use this simple example and take it into a larger context, a larger application of a hybrid electric vehicle, where the energy needs to be managed in order to determine whether power should be used by the battery, the energy stored in the battery, or the vehicle should be powered by the internal combustion engine. Let's take another look at our vehicle dynamics equations, and we can remind ourselves how they were applied in this last system model. So we have our set of forces. The driving force, F drive, which is the drive torque multiplied by 1 over the wheel radius, which gives us our driving force. This was applied via the driver block, which creates an acceleration signal in order to maintain our driving profile, our velocity profile, which sends a signal to the engine to apply this force, this torque, onto the drive axle, the powertrain. And the brake force is a signal that's sent by the driver block, the brake signal, but the actual force is applied within the right and left wheel blocks. So we saw that as a modelic force block, which applies a force in the opposite direction of the driving force. And then the rolling friction was also in these right wheel and left wheel blocks, which was a rolling friction modelica block, provided the mass of the car and the friction coefficient, and in essence it applies an opposite force, again in the opposite direction of the driving force. And then our vehicle drag, the drag force, which existed within this driving resistance block, takes into account some parameters like the cross-sectional area, the drag coefficient, and the air density. And in the end, applies another force opposite to our driving force. So the summation of all of these makes up our vehicle dynamics. So now let's see how these are applied in a more complex hybrid electric vehicle model. So here we have our hybrid electric vehicle powertrain model. And this one takes what we learned about the vehicle dynamics and then applies it into a more complex model that will tell us something about the energy management of this vehicle as it goes through this drive cycle. So let's go ahead and run the simulation. And again, it runs quickly because it's really just using more of an analytical approach rather than a 1D approach, rather than a co-simulation with 3D models. So the first output that we get here is our engine fuel consumption. So this, is a function of the work performed by the internal combustion engine in this hybrid electric vehicle. So the fuel consumption over time. And then it also, we see the behavior of the state of charge of the battery. And this being a function of the work required by the battery to produce the forward driving force of this vehicle. And of course, the battery, you see the battery usage as the state of charge diminishes. And then also this battery is being recharged at times by the engine, as happens in hybrid electric vehicles, to recharge the battery at moments to maintain, a positive state of charge throughout the drive cycle. So let's take a look inside this model and see how we get that behavior. So on the left side, we see this drive cycle that we had in the other, similar to what we had in this other model. So this is producing a desired velocity over time that that this vehicle has to maintain. And then this purple block here, I'll zoom in. This consists of, this is basically what our previous model was to a large extent. If I go inside, we go a couple levels deep in here, and then I'll open up the diagram context up in the top left here. So this is some syntax that provides us the model parameters that are used inside this equation for the vehicle dynamics. The vehicle dynamics, which will output the power required to maintain our forward drive force. So the model parameters consist of things like the mass of the vehicle is defined here, the air density, the drag coefficient, things that we remember seeing in our force equations, right? The frontal cross-sectional area, these go into the calculation of the drag force. We're going to take into account the road angle, the gradient of the road or the incline, coefficient of rolling friction, wind velocity. So all of these parameters are defined in this diagram context. And then if we look at this equation here, so we see there are two signals coming in: the desired speed, which is coming straight from our driver, the driving profile that we want to maintain. So our desired speed and desired acceleration. These are going to be two values used in this equation to output the power required. So there are a few parts to this equation, and if we pull them out, we can recognize parts of our vehicle dynamics model. So m is the mass of the vehicle. U2 is our second input, which is the acceleration. So mass times acceleration will be our desired forward force, our driving force of the vehicle. And then this second part here, I see the drag coefficient. A is the cross-sectional area of the front of the vehicle. UW is our wind velocity. So this makes up the calculation for the drag coefficient. And then this third entity here, this third entry is the frictional calculation, the rolling friction. And then the extra effort it'll take to take into account the incline of the road, the gradient of the road. So all of that will output our force required in order to maintain our desired speed. So if I back out to the top level of this diagram again, that block is outputting our force required, or our power demand. And then we go into this block that is called the supervisory controller. And so the goal of this block is to decide whether to have the battery provide the power necessary in order to produce our forward driving force, or whether to engage the internal combustion engine in order to produce that forward force, driving force. So if I look inside our supervisory controller, before we enter into it, we see that it's receiving as input the state of charge of the battery at every time step, at every moment, and also this power demand coming from our required power vehicle block. So now we move inside of this, and we see with a nice little diagram up here that this is a series hybrid system. And this, so with a little bit of logic here, control logic, This part of the system decides based on the demanded power at every moment whether to engage, whether to pull the power from the battery, power demand from the battery, or whether, because of maybe the state of charge of this battery at this moment, if it's too low, if it's under a certain threshold, it won't engage the battery. It will engage. It will require power from the engine instead. And so this is a little bit of logic that that makes up this supervisory controller of our hybrid electric vehicle. So it will either demand power from the internal combustion engine or from our battery. And this also decides whether the state of charge of this battery is below a certain threshold. It will demand extra power from the battery in order to recharge this battery, to regenerate power, stored power in the battery cells. So coming out of this block, we've got power demand from the engine, which goes into this internal combustion engine block, and power demand from the battery. The power demand from the battery goes into this our battery superblock. And if I zoom in here, we have a fairly complex set of logic and signal blocks to model this battery. But in short, it takes into account discharge losses, charging losses, and based on the power demand, the demand that we're requiring of this battery, and then also power coming from the internal combustion engine in order to recharge the battery, we're updating our state of charge at every moment. The amount of power remaining, the amount of energy remaining in this battery. And then in our engine block, we have our power demand, and then a simple lookup table that allows us to calculate or to determine the fuel consumption based on our power demand at every moment in this simulation. So the fuel consumption, the sort of immediate fuel consumption based on the power demand. And our fuel consumption goes to a fuel tank block, which really only has an integral block. So it takes a summation of our fuel total based on the changes in our fuel consumption. So an integral block is like the area under the curve. So in that way, we're summing we're taking a calculation of our fuel total throughout our driving cycle. I'll give you a couple of resources that I think you'll find useful for increasing your knowledge for system modeling and system dynamics. This one is a free ebook about system dynamics and controls using Altair Compose. And we talked about Altair Activate today, but Compose is very much underneath everything that happens in Activate, because Compose is our IDE that works with many languages, but mainly OML, the Open Matrix language. And because there is a fair amount of scripting involved in building system models in Activate, it's very good to get a good handle on system dynamics and how to model things like continuous dynamics, discrete dynamics, which we didn't really go over today, but Altair Activate is very capable of this, and so you can take advantage of that using the Compose language OML. and many other useful tools and information, and it goes down deep, and it's free to download from altairuniversity.com. And then a few other links. Altair.com/system modeling applications is the nice hub to learn more about Activate and Compose, and then to also get some customer stories and some videos about other verticals that we didn't really mention, like heavy machinery and hydraulic systems and things of that sort. You can download the products from Altair University. And we have a really nice learning center, altair.com/learning center, that you can use for nice like how-to videos and tutorials for all of our tools. And then our forum, community.altair.com. Our forum is where all of our users can post questions and answer questions for other users. And then myself and my colleagues as well answer the questions for our users. So it's a really great resource to search out anything that you're wondering or having difficulty with, and see if somebody already has provided an answer for this. So thank you very much for listening. We appreciate you being interested in our tools. We'd love for you to get going with Activate and our other tools. And if you have any questions, please feel free to reach out and visit our forum and the other resources to start learning more about how to get going using this for your projects and whatever you need. Thank you again.
All right. Well, thank you, Patrick. Again, you can ask a few questions right now of Patrick. We have him here with us, so you don't have to use the forum at the moment. But we would, so please answer the questions there. And just one thing to let you know, if you're on our student team, when we have the sponsorship, you can send email to our support line or go into our Altair community and submit a ticket, and we'll handle it directly that way, just like if you were a company. If you're a student, we can't support the 50,000 students that download our tools, so the forum is the best way to do that. And then if you have working with a class, and we can work with the faculty of that class to answer any questions that are still out there. So just something to be aware of, how to ask those questions if you have them. So again, if you're on the student team, it's great to sign up for the sponsorship, because then you can directly contact us through the support line. I don't see any questions yet. While I'm doing that, and so people can have a minute to think of something, I mentioned, I just wanted to show for those who weren't aware of how to get access to the free student edition and some other things. I'm just going to quickly show our website. So I know some of you are aware of this, but not everybody is. If you go to our website, www.altair.com/hyperworks, go to under resources, the academic program. This is where you can get access to all of those content, some of which Patrick mentioned. So if you go under students, this is where you would find how to get the free student edition, a lot of free books. There's last I counted, there was almost 20 of them that you can take a look at, hear about different things, whether it's CFD, crash, etc. Sign up for our free sponsorship right here under student competitions. If you like to do extra work, we have some projects you can look at and then use our tools on those. So this is a great center to look for things. And then we have some online learning and certification. What that certification means, it's just saying that you understood the material you covered. It's not an industry certification, but just saying I took this and I passed it, because you have to take a test at the end. We have also the learning library here, which hosts a lot of tutorials. If you go in there, you can find specific tutorials. Type in a product name or a physics you're looking for, and it'll try to find what you're looking for that. But the online learning is really a great resource, because once you make your account here, which is free, of course, and go in learning, you're able to pick from a lot of different topics, and again, some of them we just talked about today. If you wanted to see again self-paced model-based development, we have tools here, and again some other ones here about activate and compose, and some other options you can learn. So plenty of ways to learn, and in all our tools, if you go to the file and go to the online help under the file tab, there'll be tutorials there too. So plenty of ways to learn how to use our tools. I just wanted to show that so people feel a little bit comfortable what to expect if you do go to our site here, and where you can find some of this information. All right, I don't see any questions that came in, Patrick. So at this point, we are at 5:02 exactly. So we can, close today's session, and just hope everybody will attend next week's sessions that we have. We have 2 days next week. This was the long week with 3 sessions. Next week we have 2, and to go some over more advanced topics. And if you haven't, check them out, just go back to the webinar series and check the agenda here. And as you can see, as I mentioned, September 8th and September 9th recordings and mono files are there already, and they already put some of the recordings from the earlier sessions that we had from our APAC and EMEA sessions. So things are being posted there quite quickly. I'd like to thank everybody for joining, and have a great weekend. And thank you, Patrick. Thank you, Mohammed, for your wonderful presentations.